Hello, everyone. Can we start? Okay, so welcome to Physics 112. So I put one clicker question. And so basically, that's one of the themes that we will cover today. The question is, what is the type of current supplied by wall outlets, such as that one in the US? The answer is, you guys are quiet today. The answer is A, right? And anyone knows the voltage, the potential of the AC power, our power outlet? You don't know? Any guess? Okay, so it's 110 volts, okay? And sorry, you guys probably have question about exam 2. Are you guys discussing about exam 2? Okay. All right, so first, 110 volt is the potential or the voltage in the US, but it's not always like that everywhere. When I was little, the potential in my home country was 220. And my government made changes. And because of that, we had to use transformer, which is one of the things that we will discuss today. Because if you plug a device that can only take 110 volts, but you introduce that device, expose that device to 220 volt, the device will burn, basically. So we spend a lot of money around that time buying transformer or damaging our devices. So another thing that is useful about AC and mutual inductance, which is the title of today's lecture, is when you do wireless charging. So basically, when I charge my cell phone in my car, I stick it to a wireless charging. That wireless charging has a coil, which is basically another form of solenoids. And also inside my cell phone has coil. And because of these coils and AC currents, it can change the magnetic flux and also can induce currents, thanks to Faraday's law and Lenz's law. Okay. Now we have time for discussing exam 2. So basically on Saturday, my computer was smoking. I got a lot of emails from you and Zoom call, and I apologize for that. Sometimes in life, you do things, and I did tests, and we did tests after the tragedy, after the incident, and there's no guarantee that the exam that you can take today in an hour will be problem-free, but we are doing our best here. Okay. So for exam 2, okay. So for exam 2, you can take it in an hour. The reason why I do it like that, because in case you have questions, so I can answer your question before the exam. Any questions? Or one of you asked whether the problems would be similar. They are similar. I changed some of them. I split one of them. So total is still 15 points. You only need to get 14 points out of 15 to get a perfect score. I split one of them, so there are 2 problems with 0.5 points. But some of them change. Be careful with the signs, because previously when maybe it was negative, now became positive. The right loop becomes the left loop of the circuit. Maybe the circuit also change. So be careful. Don't just rely on your memory, because the goal of the exam is to test your understanding, not your memory. Okay. No question? Good. And this is the organization of the class in the next, I think until the end of the semester. You only have to deal with me for another, what, 5 weeks, 6 weeks? And then life will be normal. It's, my daughter say that by this time, all of your students must know that you're not normal. So after 6 weeks, it will be normal. And then my response to her is that, wait, okay, what is your name again? Start, yeah, 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 okay. For what? Oh, exam 3 will be in class. Unless you want it to be take home, meaning like outside class time. Okay, so back to the exam. So exam 3 will be in class, not in class, sorry, during class time, and same rules, no collaboration, closed book standard rules, but it will be during class time. Good. And I haven't checked your final exam time. Your final exam will be in May. Okay. So let's recap. I hope you still remember, because the materials that we will use, the foundational science of mutual inductance or transformers, we discussed that before the spring break. Okay. So first, for solenoid, and this is part of your exam 2 materials, if you flow without currents, without moving charges along solenoid, okay, without moving charges, there is no magnetic field, but with currents, well, my drawing is not that clear, but there will be magnetic field. Basically, this one acts as if it is a bar magnet. If you flow electric currents. Okay. So that's one. And then the magnitude of the magnetic field is, you don't have to memorize this, but it's mu naught. This is permittivity times N times I, where I is the currents. Okay, so that's one. So one thing that we mentioned in the class before is that if you have a closed surface, so this is a closed surface here, then the flux is 0. But if you have a not closed surface like this, for example, this is surface or area, then the flux is equal to, so this is the flux of magnetic field. It's always the field times area. The flux of something is the field times area, but the flux of a magnetic field is B times A. Times cosine angle. But at this point, for this lecture, this one is always is equal to 1. Okay, for this class, so I need to fix your lecture notes. There is cosine factor there. And I don't remember the Greek letter that we use. I think we use also phi. Anyone still remember this? This is part of exam 3. And then what we discussed, and then after that, so up to this point, everything, meaning like the magnetic field stays the same over time, but they can also change. When magnetic field change, in the class, we did demonstration with galvanometer, basically amp meter, and a coil and bar magnets. Basically, we can change the magnetic field it will induce an EMF. In lecture notes, I didn't spell it. EMF induce is equal to negative. This is due to Lenz's law. Do you guys still remember this? Good. Times N. N is the number of coil times change of the magnetic field. So in class, what I did is I moved the bar magnet closer and further from the coil to change the flux. Okay. That thing works. You can move the bar magnets. You can move the loop in electric generator. Let's say in like hydro power. Basically, water current driven power generator. The loop moves. But let's say if you want to charge your cell phone or your toothbrush, you don't want anything move, right? There is not much space. So one thing that you can do is you can combine this. You can combine, or you can just use phi here. So it's minus n delta VA times delta t divided by delta t, and then minus n. A stays the same, and then this one delta t also stays the same. B is delta of mu naught n times I. Okay. So at this point, if we don't want anything moving, one thing that we can do, since mu naught is one of the physical constants and n stays the same, then we need to change I. This is just a long way to say that we need to change the current of the solenoid to generate induced current or induced EMF. So how to change the currents? Well, I mean, we're lucky. In our era, we have AC. So this is an AC source or power supply. The currents for AC, basically, it oscillates. And then you don't need to memorize this. The period or the frequency in the US is 60 hertz, I believe. In some countries, it's 55, but in the US, it's 60 volts, 60 hertz. And then this is either the voltage or the currents. Okay. Any questions? All right. So I'll try to be brief here because it's kind of messy. So and I need my iPad so I can be consistent with the notation. So let's say this is a coil of your iPhone charger. Okay. And we call this, there is index, this is 1. Or in some textbook, they call it primary coil. And then let's say this is your device, toothbrush, or induction stove, a pan on induction stove. This one is coil number 2, and we call it secondary coil. Example, smartphone or toothbrush. Okay. So if we flow currents, so I'm going to be a little bit sloppy with, or very sloppy with the sign, because the current will go positive and negative. So almost there is no point of keeping the sign because the current doesn't stay the same. One thing that I forget, for currents, we will use small I for currents. I is time varying currents. And then capital I is basically current that stays the same. Okay. So if we flow currents along the first coil, it will generate magnetic fields. Let's call it B1. Is that what the symbol that is? Okay, good. And then the area for the secondary coil is A2. Okay. This one is I1. And the current along the induced current is I2. Okay. Don't worry about the sign because it's AC. It goes from positive, negative, positive, negative. Okay. So basically you have the first coil. It generates magnetic fields like the coil up there. And then the secondary coil has area. And then we can calculate the magnetic flux of coil number 2, which is B1 times A2. Okay. And this one, if you want to be exact, is mu naught N times small I. Again, I, the reason why I'm using a small letter here, because this I depends on time times A2. Basically, it's proportional to I1. Okay. What we are trying to do is we want to calculate the EMF of coil number 2 due to the first coil. Okay. So probably the formula is covered by the screen. The formula is N2 okay. This is just Faraday's law. And since the only thing that changed to in the flux is the currents, then physicists or engineers, they just come up with a constant, which is M21. Okay, M21, and the change of current divided by delta T. Okay, is that clear? And I make a mistake. I forgot to put 1. Okay. So basically, using this part of the equation here, this gives M. So N2 phi or flux of B2 is equal to M21 times I1. And then we can probably, any questions so far? Right now, what I'm trying to do is to give a definition of this M. M is the mutual inductance. At this point of the lecture, M21 is mutual inductance of coil 2 due to coil 1. So this one is equal to N2 I flux due to coil 1 in coil 2 divided by the currents. This is just a definition. Okay. And then you can read, initially this one was 2 slides. Basically, it turns out that the mutual inductance of M21, mutual inductance of coil 2 due to coil 1 is equal to the mutual inductance of coil 1 due to coil 2. So let me explain a little bit about that. So since coil 1 generate flux or generate magnetic field, sorry. Then, so coil 1 generate magnetic fields, and because I changes over time, it induces EMF, and because the coil has resistance, it induces currents, and these currents will generate magnetic fields that oppose the first, the, that oppose the blue magnetic field. Okay. So this is why we call it mutual, because you excite one. So you, let's say, put this thing to your wall outlet, and then you put your cell phone, it will generate currents and potential. You can charge your cell phone, but because there is a current, it will push back magnetic fields to the loop. But as long as you drive it with AC currents, then it should be fine. Is that good? What happened when it's DC? What happened if, okay, any guess? Let's say you don't have access to, let's say you're away from the civilization, you only have battery. What happened with DC currents? Yeah, there is no change current. And then, yeah, there is no induction. Mathematically, so Holden is correct. Mathematically, the change of currents for DC is 0. I'm not going to draw it because we are talking about AC right now. Then there is no induced EMF, there is no induced currents. Good. All right. So effectively what we did is M to 1. So M12 is N1. You can do this thing yourself. And then, and I'm not going to do it in the in class today. If you put all the numbers, because I2 is a function of I1, M12 is equal to M21 is equal to M. You will know that after another whiteboard of derivation, which I will not do today. Okay? But basically, like in that on that slide, the EMF is a function of mutual inductance times the change of the current that you put from the outlet. Okay, that's basically what I want you to know. Okay. And then there is this derivation. This is a famous device. It's made by Tesla. Oh, sorry. Well, too late. So we can just, I can just read it. So basically it's a Tesla coil. It has two coils. They are coaxial or concentric. It has N turn, N1 and N2, and certain length. The question is, what is the mutual inductance? Okay. So mutual inductance. So first, for a coil, again, the magnetic field is mu naught N times I, and N is for the first one. So there is another coil here. So the first one is N1, the second one is N2. So this one is mu naught N1 divided by L times I1. And then for M, we can do the second one, which is N2 times flux along the secondary coil. So this is the secondary coil. Sorry. Divided by I1. Okay. And the flux in coil 2 is equal to N2, sorry, N2 times the flux, which is mu naught N1 times I1 divided by L. And then there is I1 here. And it cancel. then there is A here, I forget, sorry. So this is flux. So basically this one is the flux. And then after you cancel everything, you end up with N1 times N2 times mu naught times A divided by L, okay? I'm not going to ask you this derivation. I will give you this equation on the exam. So, but this is a famous expression of mutual inductance of a Tesla coil. So it depends on the number of turns of the first coil and second coil, and then depends on the area, the size of the coil, and the length of the coil. One thing that is interesting from this derivation is that you can also derive it using the other coil, the first coil. So N1 times flux 1 divided by time-dependent currents of the second coil that generated by the first coil or primary coil. And then you end up with the same value. Okay. Good. So I think we are done with the hairy part of the lecture. Let me, now we will talk about transformer, which is the most relevant part of this lecture. Any questions so far? We have 23 minutes. Okay, so transformer, okay? This is transformer, like not the movie. This is a device. So basically, the trick with transformer is that it involves basically a closed shape of a metal. Okay, and then you can connect one side with N turned. Okay, can be more dense than the other, and the other side with less dense, let's say. And this is primary or coil 1, and this one is secondary. Okay. Or coil, so 2 and then 1. Okay. And then you can, I don't know, drive your, I don't know, your TV, let's say. You can put your device here, and you can put another voltage here. So in the case of my childhood, it was like 220 volts. We want to reduce the voltage to 110. So one thing that I forgot to mention is that what is this transformer? What is the function of transformer? Transformer, the goal of a transformer is to change voltage. And it can be from 220 to 110 volts, or from 1,000,000 volt to 110 volts. So now the question is, why do we need this iron, this conducting material? Anyone still remember from your proposal? Why do we need this iron core? People at the back. Yes, you. Yeah, you. Everyone is looking at their notebook. Uh, somebody with black sweater. Yeah, you. Why do we need this iron core? So it actually says there. So flux, initially the theory of flux was derived, was made to explain flow of water. And in water, if you have a hose, you can channel energy. You have a water flow, and then with hose, you can direct the flow of the energy. Here, the same thing. You have a flux here, and it changes over time. And because of this conducting materials or magnetic materials, the flux, so flux in one is equal to flux in the secondary coil. That's basically the reason why we put this iron core. Okay. So this one is to I don't know, to flow flux, I guess you can call it that way. Then primary, so the flux of the primary coil is equal to the flux of the secondary coil. And then from Faraday's law, EMF is equal to minus N times the change of flux divided by the change of time. Okay. Right. So anyone still remember this? And similarly for the second loop, right? Have to be careful with. Okay. So, and then since the flux of the primary and secondary are identical, that means this is identical. This part of the equations are identical. So from this, can you see this whiteboard? So E1 is equal to N1 times something, and then E2 is also equal to N2. So what we can do is we can divide the top divided by bottom, so E1, so the EMF of the primary coil divided by the EMF of the secondary coil is equal to N1, the number of turns of the primary coil divided by the number of turns of the secondary coil. Okay, or what I wrote in the lecture notes is E1 divided by N1 is equal to E2 divided by N2. So this is the formula for transformer. So with, let's say when I was young, if I want to, instead of buying transformer from a store, if I want to make it myself, I can find an iron core. And let's say the original potential is 110, and I want to increase the potential to 220 volts. Then all I need to do is to adjust the number of turns. Maybe this one is 100 turns, and this one can be just 200 turns. So sometimes if you are in a hurry, instead of going to Amazon or Best Buy, you can just find materials in your home and build transformers yourself. I did that when I was a graduate student. Okay, so this is really useful. What do we need? So other than different turns and our iron core, what do we need? Huh? Yeah, we need alternating currents. So before spring break, I mentioned that a long time ago, more than 100 years ago, there was, or maybe less, there was a feud between Thomas Alva Edison and Nikola Tesla. Tesla is a big proponent of AC currents, and Edison loves direct currents. So now, as you can see in our outlets, Tesla wins. Tesla wins simply because it's really convenient to change the voltage of alternating currents than DC currents. So this is the reason why Tesla wins. So in exam 3, I may ask you a problem that look like this. So there is a, let's send it to iClicker. So there is the circuit with two number of turns, two coils and iron core. It is driven by DC currents or DC voltage. Okay. The question is, when the switch is closed, the potential difference across R is, let's spend a minute. Oh, maybe I need to. So we just spent 40 minutes discussing about AC currents. Okay. All right. 15 more minutes. Sorry, 15 more seconds. So again, the key word is DC versus AC. Okay. All right. 5 more seconds. 4, 3, 2, 1. So let me give you another, like the 1-minute version of the last 40-minute lecture. Okay. So for a transformer to work, to generate anything at the other end, so we need an AC currents. Okay. Without AC currents, then this term will be 0 and there is no current here. Okay. So let's, any other question? So let's take another vote. Okay. And let's spend another minute, because this type of problem may appear on your MCAT. Good. All right. So it seems that you get the message. So 10 more seconds. 5, 4, 3, 2, 1. Okay, good. So 90% of you got it right. The answer is B. And then I think Eli, how to pronounce it? Eli or Eli? Eli asked this question: what happened if it's driven by DC? And Holden answered that there is no currents. Basically, the voltage is 0. Okay, so there is another variant of the problem. Not sure if this one is relevant for MCAT, but in case some of you will need it, I'm going to push this to iClicker. So we have another transformer with 2 turns. But now you're given I. I is the currents. Unfortunately, I made a mistake. It should be small letter, small I, not capital I, okay? So one turn is more dense than the other. The question is, which is the correct relation between the currents and the number of turns? Is it option A or option B? Now, we know that the flux is the same. Another thing that should be the same is the energy. Energy that is gained should be equal to the energy loss. Okay? So that means the energy per unit time is the same. So NP is energy per unit time or power. And this one is equal to E1 I1 is equal to EMF2 times I2. So that's the hint. So I give you 2 minutes. Oh, and then one thing is E1. Like this. Okay. Previously, we have derived EMF1 divided by N1 is equal to EMF2 divided by N2. Okay. 10 more seconds. Most of you actually got it right. So I'm really impressed. Okay. 5, 3, 2, 1. Okay. So let's see. All right. Good. So most of you got it right. So you can, I think here, the easiest thing to do is to do it mathematically. So E1